Allie.
Hi.
This is, and Maddie, maybe if she's watching this too, even though she's here. But anyway, section 4.1. I'm so excited, guys. I'm so excited. We're starting derivatives. Yay!
Oh,
We're past limits.
That sounds icky.
Done. Derivatives you are going to love, but you're not going to love today. Sorry. Today is explaining to you what a derivative is, but I don't, as ugly as this is, I don't skip over it because you need to know what a derivative is in order to be able to find it. So tomorrow we learn all sorts of shortcuts for finding a derivative of a function, but today you have to learn what it is, okay? So it's really super important that you learn what's going on today. This is a section that's kind of like section 3.1 where we did the homework all together and stuff. You know, it's just kind of like I want to walk you through this so that you understand what's going on. Tomorrow we'll learn the shortcuts, but this is really beneficial because you have to know what you're finding to begin with, okay? So we're finding the derivative, okay? Here's what a derivative is. Ready? If I'm looking at these three graphs right here, you see this little point that's right here and this little line that's extending off of it? Do you know what that little line is called? That's a tangent line, okay? A derivative. A derivative, write this at the top of your paper. A derivative, in its most simple form, derivatives stand for other things, but a derivative is the slope, whoa, where did he go? Slope of a tangent line, okay? Derivatives are also used to find velocity and acceleration, so like some physicsy things. But in its most simple form, a derivative, the most simple definition is a derivative is the slope of a tangent line. Now, the reason why this might be beneficial is if you're looking at this function, this first one right here, do you see that his derivative or his slope of his tangent line is a horizontal line, right? What's the slope of a line that's horizontal?
Just a number. Y equals something.
What's if it's horizontal, what's its slope?
Y equals just a number. X.
The slope, not the equation
Zero.
line. The slope is 0, right? That's sloping nothing, right? It doesn't have a slope. So what we can do is the reason why this might be beneficial is if we're given a function, like let's say our function is, you don't necessarily have to write this down. Let's say, for example, I have y equals x squared plus 5x plus 6. I don't know. Let's say we have a function like that. And we're trying to find where his high points and his low points are. Let's say down here, he's going to have a horizontal tangent line also, right? What I can do is find the derivative of this guy and say, I want to know when his derivative is 0, because that will tell me where the hills and valleys are. Does that make sense? Without actually graphing the thing, right? I can find the hills and valleys because at a hill or a valley, his tangent line is 0. His slope is 0, right? So I can find the derivative of this thing, which gives me a new function, and say that that's 0 and find those hills and valleys, okay? That was maybe over your head just a little bit, but we'll go over that again, okay? So a derivative in short is a slope of a tangent line. This guy is talking about the slope of this tangent line. At this specific point, he has a slope of whatever that is, right? At this specific point, he has a slope of this. And this is kind of like the instantaneous rate of change, okay? Through one point, instantaneous rate of change, kind of like the acceleration. So like if the speed of my car is going up like this, what at that instant is my acceleration, okay? Kind of something like that, right? Okay, so we'll get into more story problems later on. You'll see kind of derivatives in the application sense, but we're just doing by definition, just so you can appreciate what a derivative is. We're going to do by definition. There's lots of symbols involved in this next part. Just try to stick with me as best you can, okay? We talked about this at the beginning of chapter 3, and we talked about the difference between a tangent line and a secant line, right? You remember talking about a secant line?
No.
Okay, so let's go down here and let's refresh our brains. So like, let's say I have this dot right here. That's my main dot. Over there in that corner, I'm looking at this picture down in the bottom left, okay? That dot right there, and I want to know the slope of his tangent line. And tangent line is going to be a line that probably looks like that, right? That's a tangent line to that point. It's touching at one spot, going all the way across. This is my tangent line, okay? And I want to find the slope of that, which is like finding the derivative. Okay, I want to know his slope, I want to know his derivative, right? But I can't do a slope if it only has one point, right? To do a slope, you have to have y2 minus y1, x2 minus x1, right? Okay, to do a slope, I have to do 2 points. So what we do is we pick another point, right? We pick a point maybe up here on the graph, and instead of doing the tangent line, I look at the secant line through those 2 points, right? And I find the slope there, right? But let's say now instead, after I find that secant line, I move that point closer and I draw a new secant line. There's my new secant line. Which one is going to be better, the purple slope or the green slope?
Green.
The green slope, right? This slope is going to be a better slope that's going to approximate the red one, okay? Now I'm going to move that point even closer. So I'm going to pick another point right here, and I'm going to do my secant line, okay? Now that gray line, or the light blue, I guess, whatever color it turns out to be, that's going to be even a better approximation of this red slope. And the closer and closer that gets down to being, the closer it gets to that red dot, the closer the slope is going to get. Does this make sense? We talked about this before, but the more I shove that line down, or that dot down, it's going to get closer to that red line, right? The slope of that red line. And this is the limit process, okay? This directly relates to finding a limit, okay? So what we're going to do here is, let me erase all my junk here, and I'm going to show you what points they have named here, okay? So here's this. Here's my original point, which they call it C and F of C. They could call it X and F of X, right? F of X is like the Y coordinate, okay? So X and F of X. Then they want us to go over a certain amount, which they call the change of X. It's how much the X is changing. So the change of X. That's how much X is changing going over to the right. And then, so this coordinate is the constant, X plus the change of X, or C plus the change of X. It's your X coordinate plus however much you're going over. And then your Y coordinate is going to be the Y coordinate to that point. So F of C plus the change in X, or X plus the change in X, all right? So that is your coordinate points. And now we have 2 places that we're trying to find the slope of, okay? So when I'm finding the slope, what I can do is I can take this Y coordinate minus this Y coordinate, okay? All right, write this down here in this little bit right here. If I do my slope, y2 minus y1, it's like f of c plus change x minus f of c, right? That's this Y coordinate minus this Y coordinate, okay? Over the X coordinate on the top is C plus the change in X minus this coordinate, which is just C, right? So we're finding slope.
Out?
Won't the C's in the bottom cancel out? Yes, they will. That gets us to just this function right here. Do you see that? F of C plus the change in X minus F of C all over the change in X, okay? And what we want to have happen, okay, I'm going to ask you this question. What we want to have happen is as we slide this point closer and closer to this point, what happens to the change in X? It gets smaller and smaller and smaller. So it approaches 0. So what we're going to eventually end up doing is we're going to be finding the limit as the change in X goes to 0. We're trying to get it closer and closer and closer to 0. Meaning that there's no space in there, right? We're trying to slide it down to be closer to 0, and we're finding the slope, because that's what the slope is. That gives me the slope of the tangent line, okay? This is all a little bit confusing. We're going to get better later on. So we're finding the limit, but do you see why that change in X, we're trying to slide him closer and closer to 0, right? Because it gives me a better approximation. All right, let's go ahead and do an example, and we'll see kind of how that formula plays out. So we're trying to find the derivative. Okay, and I gave you the function right here. This is the function that we're graphing, 2x minus 3. Okay, that's this line right here. It's just a linear function. They made it really basic. They're making it really easy for you. And I want to find the slope at this point right here, at 2, 1. Okay, what's going to be the slope at that point 2, 1? How much is he going up and over for that function? What's the slope at this line? 2, right? Do you see the function? 2. His slope is 2. I'm going to show you how we get 2 by using the limit definition, though. Okay, his slope is 2, and here's how we get that. That's a linear function. What we're going to do is we're going to plug in, and we're going to solve for this thing right here. Okay? All right? in the, let's see, in the equation above, they had this represented as C, right? That guy was C and that guy was C. Do you see where that formula is coming from? That guy's C. But now they have C as 2. Why do they have C as 2?
For funsies, because it's the equation.
At the point 2, 1, right? So we're looking at the x coordinate being 2. So rather than putting C in there, they put 2 in this spot and 2 in this spot, right? Okay. All right. So what's function am I using? What f of x am I using? 2x minus 3, right? Okay. If we do f of 2 plus the change in x, that means we're taking this guy and we're plugging it in there, right? That's what it means. Whenever we're finding f of something, you're plugging that stuff into the function, okay? So what will this piece of it look like? 2 times 2 plus the change of x minus 3, right? That's just taking this guy and plugging it into there. Okay, that's that chunk. Now I'm going to put that in a bracket actually because we've already used parentheses. And now we're going to do the subtract f of 2. So we're going to do this part right here. Okay, subtract f of 2. That's this piece. Okay, so if I plug now 2 into that function, this is 2 times 2 minus 3, right? That's what f of 2 is. Do you see how that works? All over what? Delta x, the change of x, all right? And I'm trying to eventually find the limit as the change of x goes to 0 of that whole big long thing, which is really gross and ugly. But we're going to simplify him here in a second. Okay, I'm trying to find the limit as the change of x goes to 0. Do you remember why we're wanting to go to 0? That represents us sliding that dot closer to the actual point, right? Change of x going to 0 is sliding that dot closer, and then this is just the slope, right? The slope of the derivative, okay? So let's simplify some stuff that's in this bracket. So I can take 2, distribute it through, right? 2 times 2 will give me 4 plus 2 change of x. 4 plus 2 change of x minus 3. Okay, are we confused? No? So 4 plus 2 change of x minus 3, that's just going to be 1 plus 2 change x, right? Do you see how that works? Okay, let's simplify the stuff in the bracket. So this 2 times 2 is 4 minus 3 is 1. So then we have minus 1, right? Do you see how that works? All over the change of x. Okay, do you see how that works? Okay.
Wait, do the delta x's just cancel?
Just wait a second, we will. Okay, so things that cancel, continuing to cancel, 1 minus 1 cancels out. And then what'd you say?
The x's.
The x's cancel out, right? Okay, so now we've simplified and we're finding the limit as the change of x goes to 0 of what?
2.
2. What's the limit of that thing as it goes to 2? This is just a horizontal line at 2, right? This is like y equals 2, so it's a horizontal line straight across at 2, right? You see what we're saying? At 2. As the change of x goes to 0 on the left and on the right as we're going towards 0. What's the limit? 2. Yeah? Does that make sense? What did we say the limit was over here? 2. Or what did we say the slope was? The slope was 2, right? The slope at this point is the same as the slope for everywhere, right? Because the slope of the line is 2, it comes out to be 2. Confusion? You can shake your head yes, it's fine. Okay? This is the longhand way of finding a derivative. The longhand way. Okay? Tomorrow I'm going to give you this example and you'll just say, oh, yep, it's 2. And without even looking at the graph. Okay? But this is where it comes from. Let's do a couple more of these and then we'll kind of have the idea down. All right? So this one is saying find the slope of the tangent lines of the graph of x squared plus 1. I have a typo. At the points 0, 1 and negative 1, 2. Okay? I don't know. Copy paste was not my friend. So this should be a C right here, by the way. That little guy. Okay? So the first thing that we want to do is we want to plug 0 in. Right? Let's just do 0, 1. Let's not worry about negative 1, 2. Okay, let's just do one of these instead of doing both of them. Okay. All right. If I look at the graph, the point 0, 1 is this dot right here. And if I make his tangent line, what does his tangent line look like?
1. A straight line.
A straight line. Straight line going straight across. We're trying to find the slope of this guy. What's the slope of that horizontal line going to be? 0. So we know our final answer is going to be 0. Okay? But keep in mind that we're doing this in hopes that we don't have to graph it every time, right? So we're trying to get to 0 without graphing, all right? We know that the answer should be 0. Let's see if it comes out to be 0. So we're going to do this process again and fill this in for my function, which is this guy, okay? All right, what is C in this case? 0. We're plugging 0 in, 0 here, okay? All right, now I'm going to work on just this part right here. F of the 0 plus the change in x.
0 squared plus 1.
Okay, wait a second. 0 plus the change in x, that's what we're plugging in. We're plugging this stuff into there, right? Okay,
Wow.
so this is 0 plus the change in x squared plus 1, right? That's what he looks like. That's what his function is. We're plugging that stuff into this x squared. We still have this guy squared plus 1. Confused? No? Okay, then let's do minus f of 0. Okay, f of 0 is plugging 0 into here.
Just 1.
So 0 squared plus 1, which is just 1, right? All over the change of x. Okay, and we're finding the limit of that. The limit as the change of x goes to 0. Whew. Okay, all right. So let's simplify through some things. What's 0 plus the change of x right here? Just the change of x, right? So this guy comes out to be just change of x squared plus 1 minus 1. Yeah? 0 plus the change of x, or change of x squared plus 1 minus 1, yeah? On the bottom is
Delta x.
delta x, or change of x.
So can we
Okay.
cross out 1 x?
So can we cross out the 1's? And what else can we cross
1
out?
delta x.
One of the delta x's. So I'm finding the limit as the change of x goes to 0 of just the change in x. Okay, what does that come out to be?
0.
Why?
Because there's no number.
You're just plugging it in, right? The change of x goes to 0. You're just plugging that number in, right? At this point, we can just plug in 0 in for change of x, and it's 0, right? We have found the slope. Does that make sense? Okay. Now, if that's the case, and we know that that comes out to be just change in x after we do all that's said and done, what we can do is we can find the limit as the change of x goes to, what was the other one that they wanted us to find? -1? Ah, that's not going to work. We can't just do that. Okay, never mind. Erase what I just said. Okay, so that guy has a slope of 0, and we have found the derivative. This is just a longhand way of finding derivative. Unpleasant? Yes, unpleasant. Okay, all right, let's talk about vertical tangent lines, because you can have those also. A tangent line can cross through a function. A lot of people think that it cannot. It just like touches and it grazes and it goes off. You can have a vertical tangent line that goes through your function. That is legal. It can like penetrate your function. Does that make sense? Okay, so you can have that happen. In that case, you kind of have like it's almost like a vertical asymptote. Okay, so you have lots of limits at infinity and limits at negative infinity. That stuff happens. Okay, I'm not going to focus too much on that, because but I'm just drawing it to your attention that that is a thing that can happen. It is legal. Okay, let's go. We're going to skip example 5. Let's go to other things down here. Okay, let's go to the back side, very, very last page. Other things that can happen. I'm just going to skim through this and show you that what some of these terms and things mean. Okay, so underline this word: differentiability. Differentiability is what that is. Okay, differentiability means you can find the derivative. Differentiability means it is able to find the derivative. Now, can you find the derivative everywhere? No, you cannot find the derivative everywhere. You cannot find the derivative at holes vase, or sharp turns. Okay? You cannot find derivatives at holes, vase, or sharp turns. Okay? And I'll show you an example of that here in a second. If a function's continuous, that means it doesn't have what? Like continuity, when it says that.
Holes.
If it's continuous,
Holes everywhere.
if continuous, no holes or vase, right? It doesn't have any holes or it doesn't have any vase. It doesn't have any jumps, turns, skips, whatever. Okay? If it's differentiable, it has no holes, vase, or sharp turns. Okay, so let's look at some examples. Down here, if I look at this graph right here, is that continuous everywhere? Does it have a value for every x coordinate?
Yes.
Yes. So this guy is continuous. Continuous on all reals. But can you take the derivative at every place?
No.
So I'm going to say it's diffable. That's my shorthand version for differentiable. It's diffable on all reals except where? Except x equals 2. I cannot find the derivative at 2 because he's a sharp corner, right? Okay, again, a derivative has to do with the tangent line. So if I pick this dot right here, let's just say we try to find his tangent line. Since he's a sharp corner, how do I draw a tangent line on that? Can I draw him like this or straight across, right? He's got like a bunch of different tangent lines that we could draw. That's why he has no derivative. Because there's a bunch of lines that just touch him at one point. Does that make sense? Yeah? So, he's continuous everywhere, but you can't find the derivative at every place. That happens at sharp turns, okay? Let's go down here to this one. Okay, is this one continuous everywhere?
Yep.
Yes. Can you find the derivative everywhere?
Yep.
Yes, but even though we have this spot right here, he has a vertical tangent line, you can find the derivative everywhere. Okay, so let's go down here. This last thing, we're almost done. Last thing, if it is continuous on all reals, is it diffable everywhere? Question mark. If it's continuous everywhere, does that mean you can take the derivative everywhere?
No.
If it's continuous everywhere, does that mean you can take the derivative everywhere? No. Because you have sharp corners. Okay, now I'm going to ask the other question. If it's diffable everywhere, meaning you can draw a tangent line anywhere you want to, if it's differentiable at all reals, is it continuous on all reals? Question mark. If you can find the derivative at any place you want to, does that mean it has to be continuous everywhere? Yes, it does. Okay, so that's where it says right here, differentiable implies continuity. If it's differentiable everywhere, if you can draw a tangent line wherever you want to, that means it's continuous everywhere. Okay, if it's continuous everywhere, though, it doesn't necessarily mean you can find the derivative. Doesn't mean those places are nice. Okay, that was a lot of information. Holy cow, that's a lot of information. Let's go down to the examples. Okay, these ones are a little bit easier. Okay, 1, 2, 3, 4 especially. They want you to estimate the slope at these 2 points. You're going to have 2 slopes.
No.
This dot right here. What's the slope of his tangent line? Let's draw his tangent line first. What's his tangent line going to look like?
Right across the tippity top.
Right across the tippity top. What's his slope?
0.
0, because he's a horizontal line. Okay, now they're saying find the same thing, the slope of this line. Okay, do you see where they've drawn that tangent? Yeah, this guy right here. What about do you think is his slope?
2.
You think 2? I'm going to try to find 2 places where it crosses nicely. I
there,
see
down
right
at the
here.
bottom.
I see right here and I see right here. You see that?
No. What?
No? Let's get rid of the line. Yeah, that's what I see. I see one crossing right here perfectly. And I see one crossing right here perfectly. You see that?
Yeah.
That's what I see. I don't know. If not, it's going to be close, right?
Yeah.
Okay, so what would the slope then be?
1, 2, 3, 4, 5. 5 over 2.
5 over 2, that's what I'm going to guess, is his slope. The slope of that tangent line is going to be about 5 over 2, right? That's his derivative. So we will say that the derivative of this function at the point x2, y2 is 5 over 2. His derivative is 5 over 2. That's the slope of his tangent line. Yeah? Good? Okay, number 2.
Wait,
Let's see
so
what we
all
got.
we're doing is just write that.
For these, yep, that's all we're doing. Okay? All right, let's go x1, y1, which is actually the one on the right. So you see his tangent line? It's just going, touching, veering off. Let's find some points that he crosses at, and what do you think?
Right up at the corner.
Right up at this corner, okay?
And
And the dot itself, right?
yeah.
He could cross there at that dot itself. So let's find his slope.
5 over 2.
5 over 2.
Negative.
Negative 5 over 2. That's his slope at that point. Okay? So at that point, he's negative 5 over 2 for his slope. Okay, now let's do y2 or x2, y2. This dot right here, his tangent line, where is he crossing? Nice.
1 down from the top.
1 down from there and 1 down from here, right there.
Yeah.
Those two. Okay, so he is up
4 over 2.
up 4 over 2, I think. We could have actually chosen this point right here instead. Up 4 over 2.
So
So his
negative
slope
2.
is positive 2 because he's going uphill, right?
Why are they
Here's a
different?
slope of 2. Okay, so how does this relate to a derivative?
I have no clue.
The derivative at that point is 2. Derivative is the slope. The derivative at this point is negative 5 over 2. That's what his derivative is. Okay? Good? Let's go down to this one. x1, y1. This dot, where is his thing?
Like
Let's pick some
where
points.
it crosses.
I see this point and I see this point. What's his slope?
Down 2 over 3.
Yes. But he's actually from left to right, he's going up 2 over 3. Right, so 2/3. Okay? Then the other one. Let's find some spots for him. This dot, his tangent line. That's a lot.
Bless you.
It's missing a lot today. You're using very snaps.
Way up there.
Way up. I see way up there.
Yeah.
And I see right here.
Down 2 over 1, 5.
Down 2 over 5. Down 2 over 5. Something like that. Minus 2 over 5. Okay? Good? All right. One more graph left.
They're parallel, so they have the same slope.
Ooh, they will. They will have the same slope. Let's see if we can figure out the slope. So he's crossing really nicely. I don't know.
Right? There.
Where?
Like right there.
I know. You don't have any XY axis, so you don't really know.
Uh,
Where?
Right about in
So
the
it's
middle.
right on
kind
the
of.
X, like you see where like the arrow is on the X on this side. Go
Uh-huh.
1, 2. It's.
I see that dot.
Oh,
No,
I was
okay,
looking
guess.
at the.
I was looking at the other.
straight over at the
3,
other one.
I was thinking 3 over.
Oh, 3 over. Okay. Yeah,
Yeah.
yeah, yeah. I see that. Okay, where else?
Way down at the bottom.
Way down at this one right here?
Yeah.
Yeah, I see that one. So from that dot, you're going up how much?
I have no clue.
5 over.
1, 2, 3, 4.
So both of those are going to have a derivative of 5/4 at both of those places. They have a derivative of 5/4 because the slope is 5/4. Yeah? Make sense? Okay, now we got 2 ugly ones.
No, thank you.
Woo! Find the slope of the tangent line to the graph at the function at the given point. Okay, so this is a linear function. We're trying to find his slope at the point negative 1/8. Okay, so the formula for the limit,
-5.
the limit thing, the limit as the change of x goes to 0 is f of c plus change x minus f of c all over change x. That's our formula that we're going to use. Okay? For the first function, what's c?
C is -1.
C is going to be -1 for the first problem, right? C is -1. Do you see why that is? That's the point that we're interested in, okay? So we're going to plug this stuff in. All right, so I'm doing the limit as the change of x goes to 0. We just got to rewrite him. All right, now we want to do this chunk right here, the f of -1 plus change x. Okay, so what will that look like?
3 minus 5
Times
-1 plus delta x.
-1 plus delta x. That's what that first piece looks like. Okay, second piece, we're going to do minus f of -1. Minus f of -1 is
-3?
3 minus 5 times -1, whatever that is.
Or 9. Because negative.
No,
No, because that
No.
doesn't do
No.
negative.
8. Because it'd be 3 plus 5, which is 8, right?
Yeah.
But it'd be minus 8. Okay, we'll get to that here in a second. So I'm going to extend him across and change x on the bottom. Okay? All right, next, let's simplify some things.
5.
So the limit as change x goes to 0 of, distribute the -5, oh heavens, 3 plus 5 minus 5 change x minus, what did we say this was? 8? Minus 8. Okay. Oh heavens to Betsy. Okay.
So that's 3, 5, and 8.
3, 5, and 8 cancel out. So we've got -5 change x over change x.
1 change x, so it's just -5.
So it's -5. What's the limit as change x goes to 0 of -5?
-5.
Just -5. That's the slope of the tangent line. That's the derivative at that point. Okay? That's the derivative at that point. Okay? Good? All right. Okay. Okay. 6. What's C?
2.
2. Let's plug 2, plug 2. Okay.
So
All right.
2.
So x squared minus 9 is 2 plus change x. This one's really unpleasant. That's that junk. Minus f of 2. F of 2 is
4 minus 9.
2 squared minus 9. 4 minus 9 are -5, right?
Yeah.
Okay, so this guy's going to be -5 all over change x, and that's the limit. Limit as change x goes to 0. Okay? Okay, unpleasant.
Do we have to FOIL?
We have to FOIL.
So 4.
2 plus change x times
4.
2 plus change x.
4
4 plus
change x plus change x squared.
plus change x squared. Okay. Holy cow. And then minus 9. So I've got
-5.
-5 plus 4 change x plus change x squared. And then what?
Wait.
That's what this stuff is.
-9
And then plus 5.
Um.
I already combined the 4 and the minus 9 to make -5.
Oh.
Mallory.
Where'd you get the +5?
Okay, the plus 5 is this.
Oh.
Okay, all over change x. Ha, heavens. Limit, change x goes
Well,
to
the
0.
5s go away.
Well, the 5s go away.
And an x can just disappear.
Yeah, I can take a change x out of here, here, and one of these. Right? So what's left over?
4 plus change x.
4 plus change x. Okay? All right, I want to find the limit as change x goes to 0 of 4 plus change x. What's that going to be?
4 plus a change x.
4 plus
0.
0. We plug 0 in, right?
Why?
Because you're plugging 0 in for change x, right? So it's just 4. So the limit at that point is 4. Whew. Okay? Good? Heavens, heavens, heavens. This is crazy. Tomorrow it will get so much better.
You also do this.
So much better. Hold on to it. And we'll make a reference back to it at some point. Okay? Actually tomorrow we'll look at it and I'll show you the shortcut and then you'll look on this and you'll say, ha! I could have done that so much easier, right?
Yeah.
Okay. All right. There you go. Bye, Ellie.
Bye, Alice.
Ellie and Maddie.
And Maddie, maybe.
Bye, Sid.